Okay,
Cool.
Raul, it's on you now.
Okay, awesome. Thank you guys for having me. This paper is called How Much Unspanned Volatility Can Different Shocks Explain? And as you probably guess now, I'm going to try to answer exactly the question that is in the title of the paper. It's a solo work. It's the spin-off from my job market paper. So let me get going here. So why should we care actually about like volatility in the US nominal yield curve? So it's super important, for instance, if you're hedging interest rate derivatives, those are the most liquid most liquid derivatives traded globally. Super important if you are thinking about, for instance, risk management. If you are a large portfolio holder, if you're an institutional investor, for instance, and you want to do risk management, you care about the volatility in the U.S. nominal yield curve. Also, if you are just like allocating money across different maturities and so on, you need to build a portfolio. You also care a lot about volatility. That's super important to decide how you're going to allocate money, for instance. Do we have good models for the yield curve in general and yield curve volatility as a spin-off of that? I would say yes and no. For to a large extent, the workhorse type of models we in academia, people in central banks, and so on. We very often use the so-called class of dynamic term structure models, very often affine term structure models. Okay, these guys are like everywhere. These models are typically, they have pros and cons. There is a reason why people in academia and people in central banks love them. They have tractable formulas for yields. The financial economists use sleeps well at night because they are arbitrage free. They are super convenient for estimation. They give you model consistent separations between term premia and the market implied expectation of short dated yields and so on. However, like these models, that this class of models that are super common in empirical research and also in academia, in central banks and so on, they deliver super poor time series dynamics for the yields. They imply super sharp restrictions on how data should behave. And important for today, what is like really, really key for this paper is that the observed volatility that you see on the data, yield volatility, should be under the lenses of this large class of models, be tightly linked to the shape of the yield curve. So the shape of the yield curve is like a sufficient statistic for the volatility you should observe. This sounds a bit crazy and so on. I'll be like very specific about this. But there is a tight link between yield volatility and the shape of the yield curve within these models. So can affine term structure models account for the volatility in yields we actually observe in the data? The answer is mostly a no. And typically there is more volatility in the data than these models can give birth to. Okay, there are different approaches on how to test this, but I would say that the most typical approach, for instance, is the first one out there, where you regress returns from interest rate straddles on interest rate changes. Why do you do that? Well, because the straddles are very sensitive regarding volatility, right? When volatility changes, you have returns in the straddles moving all around. You try to regress that on movements in the yield curve to see if indeed the different shapes of the yield curve drive these return straddles and so on. Okay, so this is like the typical approach in the literature. A lot of the literature uses derivatives to test this. So, is there any room for improvement in this? I would say so. First of all, much of the papers that I just cited in the previous slide, they think about yields and so on in a pure diffusion setting. But jumps are prevalent in bond markets, and many of these papers don't accommodate that. Second, whenever you use derivatives to test something like this, to test, let's say, restrictions that these models are generating and so on, we actually know from the literature that results are a little bit mixed depending on what type of derivatives you use. Do you use at the money derivatives, out of the money, in the money? What are you using? Okay, liquidity and the availability of strikes might depend on the overall volatility itself. So using derivatives is sort of like complicated here sometimes. Okay. Also, people typically do this type of analysis on individual maturity levels. So it's a lot of degrees of freedoms for the researcher. Should I think about the volatility of the 3-month yield, the 1 year, the 10-year, 20-year, 15, whatever, it's a lot of degrees of freedoms here. But crucially, I would say that the one thing that is really missing in this literature is that people became really good at quote unquote testing and showing that there is evidence of more volatility in the data than these large class of models we're used to using can give birth to. However, people don't typically go the extra mile of trying to connect this extra volatility to real world phenomenon. It's probably not just noise. You know, the volatility we see there. If you think about yesterday, bond markets were crazy. And reason, well, Mr. Trump. Okay. So it's probably not just noise. This is being recorded, so I hope I don't get in trouble. I'm in the US right now. Anyway, so this paper is going to do two things, okay? This paper is going to have a methodological contribution, and this paper is going to have new empirical results. From the methodology point of view, this paper proposes a new test for excessive volatility, okay? So it's a test whose null hypothesis is going to be, oh, all the volatility we see in the data is actually can be created by this large class of models. Okay, it's a test for that type of condition. I will provide a test that has a number of advantages with respect to the current literature. First of all, I'm not going to use any data from the derivatives markets. Okay, I only need zero coupon data. I only need zero coupon yields data. Second, I don't need to pick specific maturities to run the test. I'll actually focus on how the composition of the American yield curve, since we know that few factors are enough to describe the evolution of the American yield curve. I don't need to think about specific maturities, so I don't need to make a choice in that. And I'll be able to characterize a time series. I'll be able to characterize an unspanned volatility factor, an excessive volatility factor that drives 2/3 of this extra volatility that these models cannot account for. So I'll argue that to understand what these models are missing, you need to understand what can drive this volatility factor, okay? In terms of empirical results, I provide some results already going in this direction. I ask the following question. Okay, after I'll give you this time series of this like extra volatility in bond markets, what can drive this? You're going to see that this extra volatility factor, it's going to spike up at the right moments when, you know, there are major crises, major events in monetary policy and so on. And I ask the question, well, empirical macro has identified so many shocks, monetary policy shocks, fiscal policy shocks, oil price shocks. If these shocks taken at face value, they're really exogenous, they're bringing exogenous variation to the table, well, that no term structure model should be able to account for if this information is really new, if it's really a shock. So how much of this extra volatility that I characterize can you actually explain with like lots of these shocks? Okay, the answer is going to be around 12 to 15% of this volatility factor, which might be a lot or might be too low depending on where you're coming from. The good news is that there's a lot to write about. Okay, so let me get going here. Let me skip the data for a second just to make it on time. Let me characterize now. I'll give you like one result here that will characterize how I run this test for you to make sense of what I'm doing. So the setup's going to be like super simple and you know, kind of standard here. There are n underlying risk factors, xt, okay? The evolution under the Q measure and the risk neutral measure is going to follow this process here where K and sigma are constant matrices, okay? Theta here is a vector of long run means. ST is going to be an n by n diagonal matrix whose diagonal elements follow a process like that. So this is very much Duffy and Pun if you know the literature. WTQ is a Brownian motion under Q, and NTQ is a Poisson process. Okay, so I'm explicitly allowing for jumps. So there is this evolution here in the back, and the short rate process, okay, the Fed funds rate, let's say, follows this process here. It depends on these XT guys, okay, and the size of the jumps are independent of the of WT and the jump process. So if this is true, please trust me, I can write the yields that I observe in the data as an affine function of the state of the underlying states, okay? I'm going to assume I trade J fixed maturities here so I can stack everything this way. In the case I can invert B prime B, which is equivalent to assuming that B is full column rank, I'll be able to invert this relation. And uncover the underlying states just observing yields, okay? So this is present in many of the models I'm talking about, this very large class of models. So the cool thing is the following. So definition one, this is, I'm just defining a quadratic variation process. This is the time series standard. You guys know what it is, okay? So this is the standard definition of the quadratic variation process. And the cool thing is the following. For any linear combination of yields that you pick, C is just a constant vector, okay? For any linear combination L, the quadratic variation process between T and T plus H is given by this equation here. It's a long equation, but what I want you guys to focus is that there are two distinct elements here. First, there is this element here that is just a linear combination of average yields. Y bar here is just a notion of average yields in this interval, okay? While the gamma guys here are just parameters that depend on like the structural parameters of your DGP. And there's the second part here that are jumps. You know, there are jumps in bond markets, and these jumps, they're doing whatever they're doing. I'm not modeling where they're coming from. The thing is, this part here, the first part, should depend on the shape of these average yields over moments T and T plus H. Okay? So this looks like something you can test. This equation 6 looks like something you can test, right? It's calling for a regression in some way. The problem is measuring the quadratic variation of stochastic processes is typically easy. You can use realized variance, right? It's a non-parametric estimator and so on. The problem is that when you use realized variance, for instance, in this context, is going to measure both parts. The part that depends on the jumps and the parts that depend on the diffusion. So you're measuring both parts. Can we tease out and identify only one of these parts? Well, we actually can. We can use bipower variation, okay? What is bipower variation? Bipower variation for a real value process MT is going to be almost the same as realized variance, but if you notice here, given a discretization of time, there is there is I here, there is I minus 1, there is I minus 1, and there is I minus 2. Okay, so if you were doing if you're doing just quadratic variation, you would square the first bracket. Here, you're doing like this product this way. A very well-known result in this literature will tell you that the bipower variation of LT, okay, is going to be proportional to that first part that depends on average yields. Okay, so if you could approximate the bipower variation and you could approximate this side, you could run a regression here, and you should expect higher squares, and you should expect significant results over here, right? So that's what you would expect if all the volatility you see on the data is actually being born from a model like this. So I'm saying here exactly what I was saying before. We can approximate the left-hand side and the right-hand side. What I do here is that I use daily data and I compute these quadratic variation measures and so on at the monthly frequency. So it's a monthly measure of volatility in bond markets. And what you could do is just regressing bipower variation measures on average yields. And you should expect high R squares and significant coefficients. Well, but why am I focusing on linear combinations of yields? The thing is that the US yield curve admits a low rank representation. So we know that, for instance, 3 or 4 factors are enough to describe the time series evolution of the US yield curve. The big important question is, what are these factors? A very common decomposition in this literature is the so-called Nelson-Siegel decomposition. That is going to write the entire yield curve as a combination of 3 factors: a long-run factor, a short-term factor, and a medium-run factor, okay? And all the time series characteristics of yields depend on the time series characteristics of these factors. So my job market paper, for instance, shows that there is extra risk premium that these models are leaving on the table only through, for instance, beta 2. The question here is, do we see extra volatility across the entire yield curve, or is there extra volatility only at the the shorter end of the curve, or the longer end of the curve, the medium end of the curve? How's that going? I don't need to think about specific. Sorry, I don't need to think about. Oh no, I don't need to think about specific maturities here. The spoiler alert I want to give you guys that there's gonna be extra volatility all across the maturity spectrum. How do we do that? Okay, so these are the factors I was promising you guys. This is a long run factor. This is a short run factor. This is a medium term factor. Don't have time to tell you how we estimate them and so on, but let me show you guys what these factors look like. For instance, this is the long term guide, this is the short term guide, this is the medium term guide. For instance, the long term guide here is going to pick up even this like secular decline of interest rates in the US, for instance, validating this notion. It is a long term factor and so on. A similar interpretation for beta 2 and beta 3. This plot here gives you the realized volatility of these guys in blue, and in the dashed orange curve here, you see the bipolar variation. Why are these curves not on top of each other? Because of jumps, okay? Because of jumps, you're gonna see, for instance, here, you're gonna see the blue one above the orange one. So what I'm gonna do, what the test is telling me to do here, what the theory is telling me to do here is running the following regression. I can compute the bipolar variation or the bipolar covariation between any of these factors on the average yields. And I should expect in this regression high R squares and significant coefficients over here, okay? I can do even like better than this, and don't worry, there are robustness checks for this in the paper. I could run a regression of these bipolar covariation and variation measures on the average realizations of these factors. And again, I should expect higher squares and significant results. Do I do that? No, I don't. You run these regressions, you should expect in this table lots of stars, you should expect higher squares, and you actually don't. You see very lower squares across the board. Why do you see 6 regressions? Because it's the bipolar variation of each of these factors and the covariation. So 6 series in total, 6 regressions. You're not gonna see a lot of stars and so on in a table like this, telling you that there is a lot of variation on the left-hand side that cannot be driven by the right-hand side. There's a lot of variation in the data that these models cannot account for. You're rejecting, in a way, the restriction I just imposed. So I said you have 6 regressions, so you have 6 time series of residuals, okay? Why don't we look at the spectral decomposition of these residuals? You can look, right? You can compute the covariance matrix of these residuals, and you can look at the eigenvalues of these guys. And this is going to tell you that the first principal component of these residuals is going to drive essentially, roughly two-thirds of, what is missing. You're getting the residuals of these regressions, sticking them in a covariance matrix, and then you compute this guy. And then there is a dominant factor here that drives roughly 60 to 70% of whatever is missing. How does this guy look like? And this is the figure I like the most in the paper. These are the realizations of this, this unspanned volatility factor. This cannot be noise, okay? Like, come on, if this is noise, it's very special noise because it spikes up during that recessions. It spikes up exactly in moments of turmoil in markets, both in the US and, for instance, in Europe as well, okay? And with like this time series at hand, the big question becomes, what is driving this? And I know I don't have enough time to give you all the results in the paper, but this is on my website. You can download this and you can play with this if you want. I think the big question is, what is driving this? One of the things you can do, for instance, is to regress this guy, and let's say on some shock you think helps driving this. For instance, monetary policy shocks. I'm gonna show you guys one table and conclude. For instance, what do I do here? I regress that factor, okay, normalizing standard deviations into different monetary policy shocks, Fed funds rate shocks, forward guidance shocks, and QE type shocks. What you find is, for instance, if you do a back of the envelope calculation, for any forward guidance event in the US that increases the short rate by 25 bips, you have 60 0.64 standard deviations more of this unspanned volatility factor. I'm out of time. I'm going to conclude here. There are a few takeaways from this paper. There's a jump robust test for the present of unspanned vol. I characterize this factor. You can play with this factor. Okay, this factor is going to be partially driven by shocks like monetary policy, fiscal policy shocks, and oil shocks. In a few years, we're going to be writing about tariff shocks, I hope. Going forward, we can allow for more sophisticated dynamics in this type of test as well. And any kind of like interesting variation, any sort of shocks you want to stick in here, essentially you can write a paper about this. Okay, I'll stop here. Thank you very much, guys.